Hi everyone, my name is Alex Klenov, and today I'll be starting part 1 of my workshop series, where I'll be sharing my techniques and experiences when it comes to cloning and DNA manipulation. I hope that this workshop will be of use to beginner and intermediate molecular biologists, as well as expert molecular biologists who want to brush up on their skills. Any resources that I mention, I will put in the description in my blog, and if you have any questions or comments, please leave them in the comments below, and let's just get right to it. This workflow has been refined to have a relatively high success rate for most applications, and it's not the fastest workflow in that there's more upfront work with purification. However, in the long run, you will save time and money by not having to repeat your cloning experiments. And I will focus primarily on overlap-based cloning techniques like Gibson, Hifi, TEDA, etc., with Golden Gate as an interesting exception. And the scope of this workshop is essentially for molecular biologists at the beginning to intermediate level, as well as experts who have been in the field for many years and just want to brush up on their skills. As with any workflow, there are caveats and limitations, and I must say that there are many other cloning methods out there, and some may or may not be better suited for your application. And at the end of the day, any method that gives you your desired clone is fair game. I've broken down this workflow into several different steps, where we will go over how to design and define our experiment. We'll go into actually preparing our fragments, assembling the fragments together, transforming your assembled plasmid, screening the colonies for successful clones, and then actually doing things with your clones. So what are the general operations that we want to do when we're cloning? I've broken this up conceptually into the number of fragments that you'll be manipulating, the actual DNA manipulation operation that you'll be doing, and then finally the technique that you'll be using to achieve that manipulation. And we'll start off with the simplest technique, where we'll be manipulating a single fragment and doing your typical mutagenesis reactions, where you can make a point mutation or a substitution within about a 50 base pair window. You can make a deletion of almost any size in your plasmid, and then you'll learn how to make small insertions of less than 50 base pairs into your plasmid. And we'll be using a technique known as KLD Mutagenesis. Then we'll move on to increasingly more complex techniques, where we'll assemble 2 and 3 fragments into our plasmid, and we'll be able to perform operations like transferring DNA from one plasmid to another plasmid in a technique known as subcloning. We'll be able to insert DNA that we've synthesized into a plasmid, as well as insert genomic DNA as well as cloned mRNA into our plasmid. In the most complex example, we'll actually be doing multi-fragment assemblies, where we'll have our plasmid broken up into multiple pieces for ease of manipulation and flexibility, and we'll see how we can do that with TEDA, with Gibson, Hifi, and Golden Gate assembly. As well, we can apply all of these different techniques as an alternative way to do substitutions, deletions, and small insertions. For the moment, we're going to focus on the simplest example of one fragment mutagenesis. So what is KLD mutagenesis? Essentially, it's a technique which efficiently circularizes blunt-ended double-stranded DNA fragments in a one-pot reaction. And commercially, it's sold as the Q5 mutagenesis kit, and although it's a very good kit, it is very expensive. The good news is that it is easily home brewed, and we will go into the recipe later. So KLD stands for kinase, ligase, and DPN1, which constitutes the enzyme mix. The kinase phosphorylates your blunt ends, the ligase ligates the blunt ends together, and the DPN1 degrades your initial template plasmid. So I've drawn out a little picture of how the reaction proceeds. Essentially, you amplify your template plasmid with your mutagenesis primers, you generate your mutant plasmid linear double-stranded DNA through PCR, And essentially the kinase adds 5' phosphates to your linear ends. The ligase knits the linear ends together, circularizing your plasmid. And finally, the DPN1 actually degrades your template plasmid that you use to generate the mutant plasmid, but does because the template plasmid is methylated in E. coli. However, the DPN1 does not digest your PCR product and mutant plasmid because there is no methylation occurring on this DNA. Let's walk through an example where we make a point mutation or a substitution inside our plasmid of interest. And it's important to note that you can make multiple mutations in your plasmid that can be contained in either one or both of your mutagenesis primers. So here's the substitution example that I've set up. Essentially, we have your DNA plasmid sequence that you'd like to mutagenize, add this specific adenine residue from an adenine to a thymine, and I've highlighted that in red. And the question is, how do we actually design the primers, the mutagenesis primers that we need to make this operation? So the way that you design these primers is you essentially want to build in the mutation that you would like to enact into your plasmid into one of your primers, either the forward primer or the reverse primer. In this specific example, we're making this little red mutation inside our forward primer, which we designed to anneal perfectly to our template, except for the red highlighted mutagenized nucleotide right there. The reverse primer is completely complementary to the bottom strand of the plasmid, and the 5' end of the reverse primer is butt up against the forward primer. So essentially, if these two fragments were, after PCR, were to be ligated together, you would not be losing any nucleotides between these two primers. So essentially, through PCR, the mutation that's highlighted in red is incorporated into your mutant plasmid, and it is now linearized due to the PCR reaction. And using the KLD enzyme mix, this linear plasmid is now circularized and ready to transform into your E. coli, bearing the mutation that you wanted. So making a point mutation or substitution is quite simple. You essentially design two primers, one forward, one reverse, butt up against each other, and you can incorporate one or actually any number of mutations in both the forward and reverse primer, as long as there's enough complementarity with the template to give you a reasonable PCR product. A deletion is also fairly simple to make, and it's important to note here that you can delete almost any size fragment from your plasmid. If you wanted to, example, trim the fat from a vector, if it has some useless sequence that you want removed, if you have a protein and it's localizing into the wrong cellular compartment and you want to remove a signal sequence, it's actually pretty straightforward. So this is the example that I have set up here. We want to remove this specific piece from this double-stranded DNA plasmid to yield this product. If you want this region deleted, demarcated by these red lines, then you need to design your forward and reverse primers to be perfectly complementary to your template sequence right beside the sequence that you would like to remove. And through PCR, you generate a mutant plasmid that doesn't have the sequence within its plasmid DNA, and then it's subsequently phosphorylated and ligated together to yield a mutant plasmid that does not have the sequence that's flanked by your forward and reverse mutagenesis primers. So if you wanted to make a small insertion, you would essentially distribute the insertion that you would want to make into either one of your mutagenesis primers that you use. The maximum size that you can actually insert is limited by what your PCR will tolerate. If you are a guru who can manage to pull off a PCR reaction with a good PCR product with a 40 base pair insert from each mutagenesis primer, then that will also work. So for this specific insertion example, we want to insert this green portion that I've highlighted here into this specific region. So the way that you actually design these primers is that, first of all, you design the forward and reverse primer to be blunt up against the insertion site. And on either the forward or reverse primer, you design your insertion sequence as a overhang that is essentially incorporated into the subsequent PCR product. So the forward primer lands and is perfectly complementary to the top strand of the plasmid, and it extends, and because your insert sequence is physically attached to your forward primer, through PCR, your insert will actually be amplified as part of your mutant sequence and will be ligated together to form your mutant plasmid. And here's just a visual representation of what's going on. Your template plasmid is being amplified with a forward and reverse primer with a insert specifically on the forward primer. And this insert bears no complementarity to your template plasmid and is sort of hanging in the breeze during PCR until you accumulate a decent amount of mutant product. So those were 3 examples of mutagenesis reactions that we can do to make point mutations, deletions, or small insertions. And next we'll go into actual overlap cloning, where we can transfer DNA from plasmid to plasmid, we can insert synthesized DNA into our plasmid, as well as inserting genomic DNA and mRNA into our plasmid. And for this we'll use techniques like TEDA, Gibson, and Hifi assembly, as well as Golden Gate assembly. Let's start by going over TEDA, Gibson, and Hifi assembly. These are all overlap-based cloning techniques, and they essentially use the same principle for all of them, which we'll go through mechanistically in just a second. But essentially what differentiates TEDA, Gibson, Hifi, and all the other derivatives are that they're different blends of enzymes with different efficiencies for both different lengths of products, different number of fragments, etc. And they vary widely in cost. For example, TEDA, which you can homebrew for cents per reaction, all the way to Hifi assembly, which can go up to $10 or $20 per reaction. In this specific example, I have an overlap of approximately 20 base pairs on either end of the insert that is perfectly complementary to the sequence of the vector arms. And all of these mixes, at the very minimum, they contain at least an exonuclease. In this case, it's T5 exonuclease. And T5 exonuclease is a 5' to 3' exonuclease. What that means is that it will chew back the 5' to 3' top strand of any double-stranded DNA fragment. So what T5 exonuclease will do is it will take this double-stranded DNA as template and just chew back these ends, essentially leaving what are analogous to sticky ends left by restriction sites. And these overlapping fragments come together and are, in the case of Gibson and Hifi, sealed together by a combination of polymerase, which fills in the gaps, and then ligase, which actually seals any nicks left over. And at the end of the day, you get a nice, complete, double-stranded DNA plasmid with no nicks in it. TEDA and a few other mixes actually do away with some of the components, including the polymerase and the ligase, and essentially TEDA relies on the E. coli repair mechanism to actually fill in and seal these gaps. Whichever technique you use, the input and the output is essentially the same. It's just the enzymes and the intermediate process that's different. Let's use overlap cloning to perform the operation of transferring DNA from one plasmid to another in a technique known as subcloning. So in this scenario, you want to take a previously cloned gene and put it into an inducible vector for protein expression in E. coli. So this is the example I have set up here. this is the DNA sequence of your favorite gene in an unrelated vector, and your favorite his tag vector that you would like to insert your favorite gene into. And I've highlighted where the appropriate insertion site that is in frame with a 6X his tag and the stop codon in this red dotted line. When you're doing overlap cloning, these are the general steps that you want to follow. First of all, you want to start off by making an in silico mockup of your final end product that you would like to make, and you are essentially going to use that in silico mockup to design all your primers, as well as to check your open reading frame, make sure that's intact before you actually design your primers and start cloning. So here's the mockup that we have for our example, where I have, in theory, successfully cloned my favorite gene into the his tag vector. So as you can see, when I check the open reading frame of the gene of interest, it is in frame with both the his tag and the stop codon. So in theory, if this is the end product sequence, then this protein should be expressed. The next step is to actually choose the overlaps for your primer design. And for a single insertion, you are only going to be choosing the left overlap and right overlap. Depending on the mix you use, whether it's TEDA, Hifi, Gibson, etc., the length of the overlap will differ. Generally speaking, you want a minimum of 20 base pairs of overlap with your insert and the destination vector. And what's nice is that you can actually design the overlaps that you will incorporate into your primers. You can design those overlaps into the primers which you will use for the PCR that you will expect to be easier. So in a specific example, I have quite a small insert, and my vector, a typical expression vector, can be 4 or 5 kb, whereas my insert in a specific case is, let's say, maybe 150 base pairs. So it's a very, very short insert. In this specific case, I know that the PCR for my vector is going to be more difficult than it is going to be for my insert. And therefore, I'm going to design the overlaps that need to exist between my insert and my vector. I'm going to design those overlaps onto the primers that I will use to amplify my insert. So here I've shown the exact primers that you would order for the specific example. Your insert forward primer has a sequence that is perfectly complementary to the insert, as well as perfectly complementary to the vector. And then the reverse primer is the same, where it's perfectly complementary to the insert and perfectly complementary to the vector as well. However, the vector forward and the vector reverse primers, the primers that we'll use to amplify the vector, as you can see, I did not design any sequence that's complementary to the insert. You certainly could extend this primer 5' and make the vector forward primer longer, and in the end this would make your overlap between the vector and the insert 40 base pairs instead of 20 base pairs. However, during PCR of your vector fragment, this portion that is not complementary to the vector that you're amplifying will essentially be hanging in the breeze during the initial rounds of PCR, giving time and opportunity for this fragment to bind elsewhere and give you other bands on your PCR gel. And this is why having an overhang on your vector primer may make it more challenging. However, you have to make the decision for what's best for your scenario. To help visualize how the primers will be used, I've aligned them to the target insert and to the target vector. So the insert primers are going to land during PCR and amplify your insert, both from the forward and reverse direction, and insert the green overlaps into your insert fragment. For the vector PCR, the vector forward and vector reverse primers are going to land on the insertion site into your vector, and they will polymerize and linearize your destination vector. Then, when you purify and combine these fragments and perform Gibson assembly, you will retrieve your final desired clone. I'm a bit late to the DNA synthesis game. However, more and more I'm finding myself that I actually get an insert synthesized and then I insert it into my plasmid of interest. Now, can you get an entire plasmid synthesized with your insert inside your destination vector? You sure can, and I would recommend you go for it if you have the resources. However, what if, for example, the synthesis company doesn't have a suitable vector that you want to insert into? Or what if you have multiple vectors that you want to insert into and you want to save money by doing the cloning yourself? So in this specific example, I have my favorite gene synthesized as an insert, and I want to insert it into my histag inducible vector. And for this scenario, you follow much of the same design steps as before, where you make an in silico mockup, you choose your overlaps, and then you design your overlaps either into your synthesized sequence or into your primers. And here you have a little bit of choice. So for this specific example, where I have my favorite gene and I'm inserting it into a single vector, then I actually design the overlaps into the piece that I want synthesized. So I tell the synthesis company, okay, make this insert with the overlaps already built in. Therefore, I don't actually have to amplify this insert with these overlaps, which would make the PCR harder. And then the vector primers that I design don't have any overlaps on them. And therefore, I get the best of both worlds, where I amplify the vector that I'm inserting into with a primer that is perfectly complementary to the vector with no overhangs. And then my insert is already pre-synthesized with overlaps. So it's very easy to combine them and do Gibson assembly. Now, if you wanted to take your favorite gene and insert it into multiple vectors, then I would actually get the synthesis company to synthesize my insert without any overlaps. And then the way that I would actually generate those overlaps is by incorporating them into my vector primers. And that way I could vary what vector my insert would be going into by changing the sequence of the vector forward and vector insert primers. However, for the simplest example, where you're just taking a single insert, getting it synthesized, and putting it into your favorite vector, in that case, simply design the overlaps into your insert and order this insert. Design your vector forward and vector reverse primers to be perfectly complementary to your insertion site, and then order those as well. Perform PCR with your destination vector as a template to linearize it, and then you'll simply combine both fragments and Gibson assemble them. So the last operation we'll be talking about is either inserting genomic DNA into your plasmid or cloning a gene from mRNA and then inserting it into your plasmid. And it's important to note here is that depending on the difficulty of the region that you're actually trying to amplify, and then the resources that you have available, you really need to start seriously considering the synthesis of your insert at this point. Because if you're trying to amplify a seriously difficult region from your genomic DNA, or you're trying to clone a non-abundant mRNA from your total RNA pool, you need to consider the cost of the reagents and the labor that it will take to achieve success in those experiments, and the cost of potentially failed experiments, versus if you had just gotten the insert synthesized at the very beginning. You need to take into account that the lowest 2020 synthesis price that I found from Twist Bioscience is 7 cents US per base pair. And if you were trying to amplify, let's say, a 1,000 base pair insert, it would only cost you about $70 USD. And when you consider how much time that you've probably spent trying to amplify difficult targets, if you could go back in time and simply spend $70 to get that insert synthesized, I bet you would. So for difficult targets, it's often an easy choice to actually synthesize your insert. And it's a question that we don't ask ourselves very often as scientists, but how much is an hour of your time or my time worth? However, if you are intent on doing these operations yourself, this is how you can approach them. Let's take, for example, if you were trying to insert an interesting promoter region in your favorite organism from the genomic DNA into a plasmid that you want to insert it into. In the simplest case, you would simply design a forward and a reverse primer that is both complementary to your interesting promoter region and has overlaps that are complementary to your favorite plasmid. Then you would simply amplify your insert, your interesting promoter region. Your favorite plasmid, you would linearize it with your vector forward and reverse primers. You would combine the two, and you would perform Gibson assembly. What I would also recommend is that you design two primers that are actually outside of your interesting promoter region. If your PCR fails for your promoter region, what you can do is you can actually try to enrich your promoter region by, first of all, amplifying your genomic DNA with your two outside primers, and then on that subsequent PCR product, you can try and amplify your interesting promoter region. In the case of cloning a gene from mRNA, first of all, you would start with an RT reaction where you reverse transcribe the poly A tail of your mRNA using an oligo-DT primer, and one that I've used recently with great success is the oligo-DT VN primer, which actually anchors your poly-DT onto the end of the primer with this V and N nucleotide, which ensures that you get anchoring at the end of your mRNA. Your mRNA is reverse transcribed, and then, for example, you can amplify your open reading frame to insert into your vector with a gene-specific portion and a vector-specific portion that will allow Gibson assembly of your open reading frame into your favorite plasmid for, let's say, protein expression. As with the genomic DNA, I would also advise designing two primers that are outside of the region that you're trying to amplify, so that in case you encounter trouble cloning your open reading frame, you can actually enrich for, let's say, a very low abundance mRNA using primers that are flanking your open reading frame, which will allow subsequent nested PCR with your primers that will allow insertion into your favorite plasmid. In the next part of the workshop, we'll be focusing on multi-fragment assemblies, where we'll learn how to insert more than two fragments into our vector of interest, as well as perform alternative methods for substitution, deletion, and small insertion reactions, where multiple of these mutagenesis can be performed in the same plasmid. Once we've got the hang of 1 and 2 fragment assemblies, then we can move on to understanding and performing multi-fragment assemblies. So why would one want to perform a multi-fragment assembly? Well, let's say you needed to swap ORFs, open reading frames, or signal sequences all at the same time, or if you wanted to take these elements and put them in new different combinations. That is why you may want to perform multi-fragment assembly. And a multi-fragment assembly is essentially just an extension of a two-fragment assembly over multiple fragments, so you'll be applying exactly the same techniques that you learned previously, just with more pieces. So same as before, you want to make an in silico mockup of your whole plasmid, and since you're doing a multi-fragment assembly, here you want to pick as equally sized fragments as possible, which are demarcated by the overlaps that you'll choose between the fragments. So here with a 3-fragment assembly, I have a hypothetical plasmid divided up into 3 fragments, fragment 1, fragment 2, and fragment 3, which are flanked by the overlaps, overlap 1, overlap 2, and overlap 3. So here's an example of primer design at one of the overlaps that I've selected, where I essentially have the forward primer for fragment 1 overlapping completely with the reverse primer for fragment 3 over a span of 25 base pairs. So you essentially select 3 or more overlaps in your in silico plasmid that you will assemble, design the primers for each of these overlaps, and then you carefully perform PCR with the appropriate primers to generate the fragments that you need. So here I've actually color-coded the primer combinations and subsequent fragment PCR products for you, and you can see how fragment 1 will Gibson assembly to fragment 2 will Gibson assembly to fragment 3, and then fragment 3 will Gibson assembly to fragment 1, which will, in the end, give you one circular plasmid. If you're doing a 4 or more fragment assembly, you can certainly try and use TEDA, Gibson, or Hifi. However, you'll find that as you increase the number of fragments in your assembly, you'll find that the cloning efficiency decreases drastically. One technique that I've found that overcomes this limitation is Golden Gate assembly, which is an efficient one-pot assembly reaction. Golden Gate assembly is based on using BSA1 restriction enzymes, which is a restriction enzyme that recognizes its recognition sequence and cleaves distally from that recognition sequence. This allows you to build in the restriction enzyme site into your primer and then have the cleavage occur outside of the recognition site, wherein the restriction enzyme actually cleaves its own recognition site out of the primer and therefore incorporates a sticky end of almost any sequence into your fragment. In this specific example, I'm showing a 3-fragment assembly using Golden Gate, and as you can see, I've chosen 3 overhangs distributed evenly throughout the plasmid. What's important to note is that the overhang that you choose must be unique in your assembly reaction. So the 4 nucleotides that you choose for your overhang number 1, in this case ATGG, cannot be used in any of the other overhangs in your reaction. So overhang 2 needs to have a unique 4 base pair overhang, in this case AATG, and overhang 3 has its own unique overhang, TCCA. You can get a list of compatible unique overhangs in the specific supplemental material in a paper that was called Comprehensive Profiling of 4 Base Pair Overhang Ligation Fidelity by T4DNA Ligase and Application to DNA Assembly. And it's within the supplemental material, but I've just taken a snapshot right here. Fragment 1 will be generated with F1 forward and F1 reverse primers, whereas fragment 3 will be generated with fragment 3 reverse and fragment 3 forward primers. So after PCR with these primers, you're going to have fragment 1 and fragment 3 with both the overhang and the BSA1 restriction site built into it. And after digestion, you are left with a set of sticky ends which anneal and are ligated in the one-pot reaction. And you have to imagine that the same thing is happening at overhang 2 and overhang 3 if you combine fragment 1, 2, and 3 in the same reaction. Since all 3 overhangs are unique nucleotide sequence, that means that this plasmid can only be assembled in one way in the one-pot reaction. I found that this Golden Gate assembly is really excellent for assembling large numbers of different fragments in very large plasmids, and in many ways I found it to be superior to Gibson assembly in these specific applications. Where multi-fragment assembly really shines is as an alternative mutagenesis method to KLD. As you remember, KLD relies on the PCR of the entire plasmid in one go to make a substitution, deletion, or insertion. And when you're talking about large plasmids, which have intermittent regions of AT and GC rich regions, this can present quite a bit of a problem. As well, what if you want to do mutations at multiple sites within your plasmid? Essentially, you break down the problem into multiple fragments where you enact those mutations in multiple fragments of your assembly. This technique is broken down conceptually in the manual Improved Methods for Site-Directed Mutagenesis Using Gibson Assembly Master Mix. So essentially, this manual shows you that you can enact multiple mutations in multiple locations in your plasmid by simply amplifying multiple fragments with your mutations enacted in the primers that you use for PCR and then subsequently assembled through Gibson assembly. So here's a specific example of making a substitution mutation at a specific point, highlighted in red, and you essentially just build in the mutation in the two primers that you're using for Gibson assembly in the overlapping region, such that after PCR, your fragments are amplified with the mutation in the overlaps that will be chewed back by T5 exonuclease and then filled in by the polymerase and ligase in the Gibson assembly mix. Deletions can also be performed with Gibson assembly at multiple points inside your plasmid. In this specific example, we are deleting this region, and the way that you do it is that you design your forward primer or reverse primer with an overhang that actually flanks the deletion site but does not include the site that you want deleted. So essentially you amplify one fragment and another that are overlapping with two regions that are excluding the region that you want to delete. And then after Gibson assembly, you essentially delete the region that you didn't include in your overlapping primers. And finally, you can also use Gibson assembly as an alternative to make small insertions of up to 50 base pairs if you distribute the insertion between your two primers. Essentially what you do is you design your insert onto your primers that anneal blunt end against your insertion site, where your insert is actually hanging in the breeze during PCR until it's incorporated in PCR into your two fragments that you will assemble, and then through Gibson assembly, you will have that insert enacted into one or multiple spots inside your plasmid. So congratulations for sitting through that whole 40 minutes. I hope that you learned how to design your primers and your fragments. And in the next part of the workshop, we'll be going into how to actually perform the PCR, purify your fragments, how to troubleshoot, and that sort of thing. So thank you for watching, and I'll see you in part 2.